Hi everyone. My name is Jerry, and I will be your TA for CSE 215 R03 recitation. My email is as follows, and my office hours are Thursday from 3 to 5 p.m. if anyone ever needs. So before we get started with the contents of this recitation, I just want to go over how recitations generally work for this class. And so throughout the recitation, we will be going over textbook problems that go over the class lecture material covered, say, in the previous week of the lecture and such. And these will be very similar to the homework problems that you will be seeing, and they will go over the class material very well. And so they provide really great practice material that would enhance your understanding of, say, like the course content. And therefore, I also really highly encourage you to try the problems on your own as I go over them. And also, throughout recitation, of course, I would be more than happy to answer any questions. Interrupt me if there's something that you don't understand or anything. But of course, this is a recorded video, so can't really do that. So let's dive into it. So we really begin with section 1 in the textbook, where we are introduced to the concept of propositional logic, and it is really the application of the reasoning of true or false values applied towards sentences or compound sentences joined together, and they are either true or false. So we know that we can symbolically represent sentences using symbols. So let's check out problem 6 in section 2.1, where we can try to write the following statements utilizing the symbols to describe the statements below. So S, the stocks are increasing, and I's interest rates are steady. So for stocks are increasing, but interest rates are steady. But might be a tricky word in this case. But in this case, it indicates that stocks are increasing and interest rates are steady because they both happen at the same time. So for this one, the answer is simply S and I. So now we go to the second problem, part B, where it is neither the stocks are increasing nor are the interest rates steady. And if we really think about it, what this is really saying is the stocks are not increasing and the interest rates are not steady. So we can write this as the negation of S and the negation of I. So now we know how to represent sentences utilizing logical connectives and symbols and such. And so we see that we encounter variables of this form, say x and y, or x or y, basically two sentences that are joined together by one logical connective. So what happens if we want to take the negation of those? So the De Morgan's laws, they provide a closed form formula for negating the negating statement that is in the form of x and y, or x or y. And they state that the negation of x and y is equal to the negation of x or the negation of y, and the negation of x or y is equal to the negation of x and the negation of y. So what basically De Morgan's law state is that if you are negating a statement of one of these two forms, what you do is you negate each of the individual within and flip the connective. So if it's an or, you turn to an and. If it's an and, you turn to or. So let's see this applied to a problem. So Hal's a math major and Hal's sister is a computer science major. And we are to use De Morgan's laws to write negations for the following statements. So let Hal be H. I'm lazy, so I'm just simplifying. And Hal's sister, let's make it S. It is a computer major, is Hal's sister. So we know that the statement here is H and S. And so, however, if we are to apply De Morgan's laws to the statement, then we can turn this into the negation of H and S is equal to the negation of H or the negation of S. So if we are to interpret this in the context of this statement, So the negation of H is Hao is not a math major. And we have the logical connective or Hao's sister is not a computer science major. So let's also try this for the second problem. So the connector is loose, connector. Let's make this equal to C. And machine, let's make this M. So we have C or M as represented by this statement. So then if we negate C or M, this becomes the negation of C and the negation of M. And if we translate this to natural language, this implies that the connector is not loose and the machine is plugged. And that is how we utilize De Morgan's laws to solve these problems. So, um, now we go into like how to utilize truth tables and utilize it to express the truth value statements. And so truth tables are tables that we draw, such as these, involving say variables. I'm just going to make this 4 rows to establish a basic truth table for two variables. And so if you have, say, n variables, there would be 2 to the n rows. Because with each variable, there is either a true or false value. And if you guys have ever taken any combinatorics, that means that with n, there's 2 choices at every step. So there's 2 to the n rows. So let's say we have values q and r, and we want to evaluate q and r. So what we do is that we draw like this, TTFF, and what we do is we do 2 to the n minus 1 truths and 2 to the n minus 1 f's. For the next one, we do 2 to the n minus 2 truths. So in this case, it would be TF, TF, and we alternate like this. And so what truth tables really do for us is that it makes it very simple and elegant to evaluate logical statements in an organized way. So let's check out problem number 44. So what truth tables also do is that for complex statements, if two complex statements have the same truth value in every row of the truth table, then they are logically equivalent. So let's see this in practice. So assume x is a particular real number, x less than 2, or is not the case at 1 less than x less than 3, x less than or equal to 1, or either x less than 2 or x greater than or equal to 3. So already we know that these statements revolve around these three conditions, or at least these. So suppose we have a number line, 1, 2, and 3. We know that all truth values rely on these three turning points. So we can simplify this statement down to say, let's make A to be the event that x is greater than 1. And let's make B be the event that x is less than 3. C is the event that x is less than 2. So then we can rewrite the statement A as x is less than 2, which is C, or it is not the case that 1 less than x less than 3, but we have x is greater than 1 and x is less than 3. So it exactly describes the condition that these two conditions cover. So it's the negation of A and B. And that is what this is. For this one, we have x is less than or equal to 1. So it is the negation of A, or, and let's have a compound statement here, either x less than 2 or x is greater than or equal to 3. So we have C, or the negation of B. So this might take a little bit of work, but Let's see how this plays out in the truth table. So we have A, B, and C. So we have T, 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 F, 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 T, F, T. Wait, no, sorry. T, T, F, F, T, T, F, F, T, F, T, F, T, F, T, F. So we can begin by evaluating the first part, or at least the first compound part of this statement. And we can do so by trying to evaluate the negation of A, or actually, let's just begin with A and B. So A and B, in this case, would have truth values of considering here A and B, and the truth table for the and statement is as follows. What in the world is this? So true F, 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 and it is only true when both are true. So now we go back to the truth table here, and we see that A and B is true. This is true. A and B are true. This is true. And everything else is false because it has a false entry somewhere here. And so and then we take into consideration the negation of A and B. So we negate every value here into FF T, 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 T. And this is the negation of A and B. See, erase this, erase this. So now we can then evaluate C, or negation of A and B. So one of these has to be true. And again, I'm not going to write out the truth table, but basically one of these has to be true for this to be true. So we can already see that this would result in true, 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 true for this because these are true. And C, this will be true and this will be false. And we are done evaluating one of our main ones here. So here, let's try to evaluate this compound statement here now, this part. So let's do C or not B. And so I'm also just going to speed through this. I'm kind of skipping a step in negation B, but because it's one variable, it's easy enough. So this should be T, F, T, 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 no, wait, this is enough. My bad. T and T. And so then we evaluate the final row. Again, I'm skipping a step here because negation of one variable is easy enough to do. And so in this case, we get T, F, T, 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 and T. And so this column and this column are the ones that we want to consider. And so we see that since each row in this is equal, the statements are indeed logically equivalent. And that was quite a bit of work, but we can see that we simplified these into three variables that indicate the conditions. We put in a truth table and we evaluated some very relatively complex statements with a truth variable. So that's that problem. And really, truth tables are very important. So let's just do a couple more examples. With problem 5, we have negation P or Q implies negation Q. Oh, right. And this is also a good chance to go over the concept of if and then. So the conditional describes events, say if X, then Y. And the truth table is as follows. So give me a second. X, Y. And we use an arrow to indicate if X, then Y. So if X then Y is only false when X is true and Y is false. And we can take a little time to think about why that is the case. So if X then Y kind of implies a relationship that if X the condition happens, then Y must happen. So obviously if X is true and Y is true, if the X and Y is true. And if X is false and Y is false, well something uh, the condition is false, meaning that the result is false, is obviously also true as well. But here's the tricky part. So if X is true and Y is false, then the result is false, indicating that then this should definitely be false. But why does X being false imply that if X and Y is true? Well, if we think about it this way, just because the condition doesn't happen doesn't mean the result necessarily doesn't happen. And so it's like, okay, we don't necessarily know that one indicates the other, right? So if we don't know that, then the true value of this is true by default. So let's see this apply to a compound statement like negation P where Q implies negation Q. So we have two variables here, so four rows for the truth table. So we have P and Q here. And so we have T, T, F, F, T, F, T, F. And so I'm also going to again skip another step here. Usually you would do negation P with its own row, but again, one variable I'm going to skip a step here because I'm just I guess slightly lazy. I don't know. So negation of P or Q, the truth values here would be T, F, T, T, I believe. Yeah. And the negation of Q, I just love how I said I skipped doing negation of one variable, but just goes on to do the negation of this one next, but that's fine. Ft, Ft. And so then the negation of P or Q implies the negation of Q. In this case would be Ft, Ft, I believe. And true implies false is false. False implies true is automatically true. True implies false is false. True implies true is true. So this is a truth table for number 5. So now we go into a truth table of 3 variables. And remember, the number of rows for a truth table is 2 to the n because there are 2 possible values for every variable. So we have P, P, P. P, Q, and R. So truth values will be T, 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 F, 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 F. And I write it out in the pattern of 2 to the n minus 1 times, and then 2 to the n minus 1, repeating again, 2 to the n minus 2. Now 2 to the n minus 3. Okay. So now we evaluate negation Q. So not Q is F F T T F F T T. So now that we have not Q, we can evaluate P and not Q. And that should be F F T T F F F and F. So now that we have this part, we can then calculate P and not Q implies R. So automatically we see that any row that has false is automatically true in this row. So now we see true implies R, which is true. This is true here, and this is false. And that is our truth table for 7. And now let's try another one. So P, not a Q, P, Q, R, T, 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 F, 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 T, 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 wait, T, T, F, F, T, T, F, F, T, F, T, F, T, F, T, F. So what we can immediately do is, again, I'm also going to just skip a step in validating negation of R here. So I can go P and not R. So just imagine that every row in R is reversed. So then we calculate P and not R. True and false is false. True and true is true. True and false is false. True and true is true, and everything else here is false because P is false. So then we have Q or R, and one of these has to be true, so true for it to be true. So true, 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 and F, F. And so then we have P and R implies Q or R. So basically, it's this row implies this row. I mean, this column implies this column. So anything with the F is automatically true. True, true is true. F is true. TF is false. True, 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 and true. Oh, my bad. This is biconditional. So again, biconditionals are only true if and only if. Okay, well, if like say you have A biconditional B is only true if you have F, F, or T, T. So basically A is logically equivalent with B. So that is, I just realized actually the same symbol, but you guys know what I mean. So F, F, and T, T, that's the only way this will be true. So my mistake. I completely did not see that this is biconditional. So in that case, this is false. We have a true here, and this is a false, 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 but this is true. So in the textbook, or presumably in the lecture, we learned about the concept of contrapositives. And so basically what the contrapositive is that if we have, say, a statement A implies B, then the contrapositive would be, and the negation of B implies the negation of A. And so what we're told is that the contrapositive is logically equivalent to the regular conditional. So now let's use truth tables to actually establish that. So then we have Q. Let's actually just use A and B just for simplicity of letters. So again, we have A implies B, and the negation of B implies the negation of A. So here we have T, T, F, F, T, F, T, F. And so then we have A implies B. So we have T, F, T, T. And so then we have negation of A, which is FFTT, negation of B, FTFT. So the negation of B implies the negation of A is also T. True implies false is false. False implies true is true. True implies true is true. And so we see that if we consider the columns here, every row is equal, implying that the contrapositive is logically equivalent in its own way. Not in its own way, they are just logically equivalent. Anyways, so now we move on into how we can apply contrapositive to, say, natural language statements. And so let's directly jump in. So for this problem, we have rewrite the statements in 34 and 35 in if-then forms in two ways, one of which is a contrapositive of the other. So basically, what we have to do is we have to translate the sentence into either a contrapositive form or the regular if-then form, and then write the other one from our interpretation of that. So we have the Cubs will win the pennant only if they win tomorrow's game. And usually in language, we see some certain paradigms and word choices. So I want to know that if we see the only if, this means that, so usually if, and then we have a condition, and then a result. So if we see something like only if, or something is a necessary condition for the other, well, I want you guys to think that these are very strongly toned words. And so basically, if condition is false, result is false. So let's see. This would be the condition. This is the result. So we have, if we utilize that understanding, therefore, if the Cubs don't win tomorrow's game, then the Cubs will not win the pennant. And so now we see that we have a negation of P implies a negation of Q because we have these in not, don't, and not forms. So then we can reverse it by saying that the contrapositive of this is then Q implies P. So if P is the Cubs, so the Cubs win tomorrow's game, and then Q is the Cubs win the pennant, then we can reverse this to also say if the Cubs win the pennant, then they must have won tomorrow's game. Similarly, we can also go on to 37 through 40, and well, here we also introduce the concept of a sufficient condition. So what we just had was a necessary condition. If the condition doesn't happen, then the result will not happen. But if we have something that is a sufficient condition, then we have if condition happens, if C, then result will happen. And that's basically two of the main forms of paradigms that we see within statements and how to translate them to if-then forms. So we have payment will be made on the 5th unless a new hearing is granted. So a hearing being granted is sufficient for payment to not be made on the 5th, if that's the case. So, or we can also say that if a new hearing is not granted, then payment will be made on the 5th. So the answer for this one would be if a new hearing is not granted, then payment will be made on the 5th. And actually, I believe this is a case of, say, a necessary condition. So, hmm. So a new hearing being granted is a condition for payment to not be on the 5th. So if a new hearing is not granted, then payment will be made on the 5th. Okay. And in 40, we see a case of the sufficient condition. So if condition, then the result will happen. So we see that condition is this, C, and being on time for work is R. So we can simply write this as, if I just erase this, so if I catch the 8:05 bus, then I will be on time for work. And that's all it is. So what we can also do in this case with like interpreting statements into if-then forms is that we can also write the contrapositive of those, and therefore we would have two ways of writing them. So we can try this problem where we have being divisible by 3 is a necessary condition for this number to be divisible by 9, and we see that there's a necessary keyword here. So this being divisible by 3 condition, the number to be divisible by 9 as a result. So since we see that this is a necessary clause, if a number is not divisible by 3, then it is not divisible by 9. And any, like, say, number theorists in this class or like math enthusiasts will know that that is clearly not the case, and therefore we probably interpreted this correctly. And so then we have another one in the contrapositive form, which is negation of P implies negation of Q. And so if P is being divisible by 3 and Q is to be divisible by 9, then we can reverse this into contrapositive into Q implies P. And therefore, we can say that if a number is divisible by 9, then it is divisible by 3, and any of you mathematicians would also know that that is also the case. And so finally, we have another way of wording something, which is that a necessary condition for S is R means that R is necessary condition for S. So a sufficient condition for John's team to win the championship, in this case, this is the result here, winning the championship, and that it win the rest of its games is a condition. So this is a sufficient condition, which means that we can directly write if the condition, then the result will happen. And so therefore, we can solve this as if the team wins the rest of its games, the team will win the championship at the end. And so basically, that covers all of the recitation material that we have to go over today. Thank you guys, and I hope to see you guys soon. And I hope everyone's having a great vacation. Thank you.